Hello, everyone. So we're going to talk a little more about the mean and the median in this video. And I touched on this a little bit when I introduced them, that the median, one advantage the median has over the mode, over the mean, is that it tends to be resistant to outliers. Okay, outliers, remember, are pieces of data that are very, very different than our typical pieces of data. So that is kind of a nebulous definition. We're not going deep into studying outliers in this course. There are various rules of thumb, but there's no set rule to say this is an outlier and this isn't typically. But we'll discuss them on occasion as we go, and they'll certainly come up in this video a couple times. So let's start with a little graphical demonstration of one of the differences between the mean, the median, and the mode. So I'm sharing a little graph with you, and let me explain it, and then see if I can get this tablet to work correctly and annotate this a little bit. So I've got a little graph here, and these over here, these blue dots are my data points, right? So I've got a data point at 5, I've got a data point at 4, 3, 2, and 1, and down to 0. Okay, so the y value of these data points, sorry, the y value of these points represents the data, like what the value actually is. So this is a collection of data that has one data value is 0, 1, 2, 3, 4, 5. And there's a green and an orange line. You can only see one right now because the green line is below, sorry, the orange line is below the green line, but they represent the mean and the median. The green is the median, the orange one you can't see is the mode. At this point, they're both the same, 2.5, right? So the mean, remember, we would add these 5 numbers up. 0 plus 1 is 1, plus 2 is 3, plus 3 is 6. I feel like I lost track. 10 and 15, and we're dividing by 6. So we get our 2.5. That would be the mean. And the median is pretty easy to see in this. It splits the data in half. There's 3 on top and 3 in the bottom. So what I'm going to do is I'm going to play with this top piece of data, right? This piece of data right here, I'm going to change it. Okay, so I'll leave that little marking there so we remember where it was. And first I'm going to do is I'm going to raise that piece of data, right? So I'm making that, I've switched it, let's just go all the way up to 10, okay? So I've moved that piece of data that used to be down at this red arrow, and I've moved it up to 10. Notice the median hasn't changed at all. It's still the middle number, 2.5. There's 3 data on top, 3 data on the bottom. It doesn't care how far away this data point went, right? It's still in the middle. Meanwhile, the mean has gone from 2.5 up to 3 1/3, right? So remember how we computed the mean. We added 0 plus 1 was 1, plus 2 is 3, plus 3 is 6, plus 4 is 10. When this was 5, we added 5 and we got 15. Now we're adding, instead of adding 5, we're adding 10. We get a total of 20 that we divide by 6, and it becomes much higher, right? 20 divided by 6 is 3 1/3. 15 divided by 6 is 2 1/2. And so our mean has gone has changed, while our median hasn't at all. Let's take this data and move in the other direction. All right, so notice the median still hasn't changed. Now I've made this data value that was 5, I've brought it lower, and we can see that the mean, that orange line, is getting lower and lower. The median doesn't start changing until here, right? Because now it's still splitting the data, but some of the data, it's splitting between 2 numbers that are now, that top number is getting a little closer, right? This moved piece of data has moved into the middle and become part of that computation. And watch what happens as we move down. That median is staying in between this data value here and the data value I'm moving. But once this data value gets beyond, it's no longer in the middle, the median stops moving, and now only the mean can move. So I'm moving that data value all the way to -10. We can't see it anymore. So we've managed to move the median a little bit. It moved from 2.5 to 1.5, right? It moved from, it was previously the mean and the median were right there when we started. It's now moved down to here, but the mean has moved much further, right? That -10 value is canceling out all the other values when we add them together, and we're getting a mean of 0 in this case. Okay, so that's a big one of the big advantages to the median, right? Is that it's resistant to outliers. It doesn't mean the mean's not important. We're still going to have plenty of opportunities to use the mean. We just have to be aware of some of its weaknesses, and we'll discuss that later. It's obviously very important, and there's a reason that we use it so often. Why the mean or the average is so common. All right, let's do something else now with the mean and the median. So let me share some new data with you, some new images. Here we go. So I'm just looking on, in fact, sorry, I want to move these other ones off the screen so we don't have to be disturbed by them. I'm only right now concerned with this data on the left. So one more should do it. Okay, so we're just looking over at this data here. So what I have right now, what you should recognize is we've got a histogram, right? And the histogram is temperature at birth. And notice I wrote n equals 130. This is something pretty common that you'll see. N is typically what we use to mean the size of the sample. So this is data from 130 births. I have a link here, although I discovered today this is data I've been using for a while. The link is now broken, so I probably shouldn't consider this real data since I don't have it verified somewhere. So, but it's fine. I'm just using this for demonstration purposes in any event. So you'll see there's a list. I put it in order of a bunch of data. Births, the temperature of babies at birth in degrees Fahrenheit, right? So you can see, if we look at this histogram carefully, it's a little crowded, but you can see right around 98 degrees is where we're getting most of them, right? Our bucket sizes, our class sizes here are 0.4, so between 98.2 and 98.6, we can see that there are 37 births with that temperature, and you can see nearby there's some bars at 19 and 20 and 21, and as we move further away there's fewer and fewer births at those weights. Okay, so before we move on to discussing the mean and the median, let's just notice that we see a familiar shape here, something I've mentioned in the past briefly and we're going to be discussing at length shortly, is this sort of shape, right? So this curve is not matching up perfectly, of course, but this idea, this is normally distributed data. So that phrase might not mean much yet, but it basically comes down to the idea that we have data that is clustered near the mean, clustered in the middle, with less and less data as you go further and further away. Okay, so this is a pretty familiar picture right here. Okay. So what I'm going to do, one more thing I want to show you on this. I've created a little table up here that is computing the mean and the median for this data. Okay, so the mean is 98.249 and the median is 98.300. They're very close to each other. This is pretty typical for data that is what we call symmetric, meaning an easy way to think about it is you could fold it over the middle. Right? If you drew a line down the middle of this data, right, about where, so pretend I'm good enough with this thing to draw straight lines and get it right where I want it in the middle there. If we fold it over, it's not a perfect match, but it's pretty close. So this data is not perfectly symmetric, but it's relatively symmetric. We'll talk a little more about that in just a few minutes, this idea of symmetry. What I really want to show now is similar to that graphic demonstration I just did, what happens when we add data, especially outliers, to our data sets. So I'm going to add some data here, and what I want us to watch is what happens as we change the mean and what happens as we change data to the mean and the median. Okay, so the originals, these won't change. These are just here for reference. As I add data, these are going to change because my computation is including these cells. So let's just add some data in. So first I'm going to add a little bit of, I'm just going to add some data at the low end of our histogram, so values of 93. So I'm adding in all 93s. And we can see on our histogram, automatically sheets updated to show that there's now some data sitting down here, right? Just from this picture, this might suggest that these are outliers, meaning they're very different than everything else, right? You just look at this and go, what's going on there, right? And we'll talk about what that might be in a second, but let's look at our mean and our median, right? The median went from 98.3, the original number, to 98.2. So it lowered by 1/10. This did have an effect on the median. However, it's not nearly as much as, right? It lowered by 0.1. Our mean has lowered by about 0.3, okay? A little less than 0.3. So more than twice as much effective change on the mean than the median, right? So again, here's the originals, and here, this column E shows the original mean and median, and here we see the current after putting in this new data, and we see there's a much bigger effect on the mean. Let's try going in the other direction. Let's add in some temperatures of 104. Let's make them 103.9 so they show up on our histogram. So there's these 103.9 temperatures, and we see a very similar thing. In this case, the median didn't change at all, right? It stayed exactly the same, or at least the same up to 3 decimal places. And our mean jumped up again by about 0.3 degrees, right? And a third of a degree, about 3/10 of a degree might not seem a lot, but notice how much there's not a lot of change between these degrees, right? Without this fabricated data, our smallest is 96.3 and our maximum is 100.8. So there's only a few degrees difference in all of this. So 3/10 all of a sudden becomes a significant leap, right? And so that mean jumping by 3/10 is actually pretty meaningful, right? And now let's do one more example before we discuss outliers here. Let's make a more extreme example. Let's put in something like 80, okay, right? Which is a ridiculous, which is not a realistic temperature. It doesn't even show up on our histogram here. And notice how much lower the median has only lowered by 1/10 again, whereas the mean has now lowered a couple of degrees, right? With these 1, 2, 3, 4, 5, 6, 7 temperatures, right? Now, if you're a doctor or scientist doing this study and you see that there are these births at 80 degrees, you might be suspicious, right? This might jump out and say, wait a minute, that's way too cold for a child at birth, right? The child's going to be pretty close in temperature to the mother, right? They've been intertwined all this time. There can't be a heat sink in the middle of her belly. So you might think there's something wrong. Maybe this represents a day where maybe these 7 values are where somebody made an error in typing values into your sheet, into wherever you're storing data. Maybe this represents a day where there was something broken in the thermometer, whatever it could be, right? Some little error in data collection, okay? Now, this doesn't seem like a big deal. I think if you were doing this study, you would be able to notice that these temperatures, there's something broken. But what if you're doing a study where you don't already know the human temperature, right? In this case, we're all expecting something around 98 degrees Fahrenheit. And so getting 80 degrees jumps out at us. If you're studying something brand new and there are some errors, right? This shows you how much just a handful, 1, 2, 3, 4, 5, 6, 7 misentered data values can affect the mean pretty significantly. And if you don't know that those are errors, if there's nothing obviously errors about making them be errors, if you're studying something you don't have a lot of information about, you're not going to catch that. And so that's a case where the median, even though it did change a little bit, you're not throwing off your results nearly as much because of these outliers, right? And that's often what outliers end up being. Sometimes there's a reason meaning a reason that's important to understand, but sometimes the reason is something unrelated to what you're studying, like this might be a broken thermometer or simply an error in data entry, right? Which shouldn't affect your scientific results. You go, oh, we're gonna throw those out, right? That's often the case with outliers. Are you deciding to throw them out because they're useless, or are they interesting cases where something extreme has happened? And that's something you have to decide on a case-by-case basis. Okay, one more example here. So same sheet. Now I've got some data that I made up, or at least had a computer generate for me. So I've got 30 pieces of data here and a histogram, and I've made this histogram to appear perfectly symmetric. Okay, that's fabricated. Data rarely comes in perfectly symmetric. Although I would say this is not actually perfectly symmetric because there's the data within these bins can vary a little bit, but it's essentially symmetric because of how close it is to this. So we're going to do a similar kind of game that I just did with adding data and seeing what happens, but we're going to have a little bit different of a focus. So what we're looking at here, before I start changing things, here's my mean and my median. Oh, and I just realized I have forgotten to put in the current and original. It'd be nice to be able to compare them. Okay. I don't like one being 2 decimal places and the other one not being that. So hold on, let me satisfy my let's see, first let's put it in the middle. I'm going to format the numbers to be 2 decimal places. Okay, so anyhow, here is our data. There's the original mean, and I'm about to change them, so we'll see this current mean and median change as I go forward. Okay, so what I want to do, I'm going to take some data from the top of this histogram and move it to the bottom. In other words, I'm starting with a symmetric histogram, but I'm going to take data from the top end, the higher values, and move them to the bottom end. In other words, I'm going to change these values. So for instance, I can change the value 14.4. Let's change it to something like 6. Maybe I'll change this one to 4. Maybe I'll change this one to 3. And let's do one more. Let's change this one to 4.5. Okay, so if you looked at what was happening with our histogram, the bins over here were slowly disappearing, and we were pulling data over here to the left. Okay, so few things we're going to notice. First of all, we call this. I'm going to try to write now with my little tablet, which has been giving me mixed results. We call this skewed left, right? Because we've taken data from the right side, right? We had all this data over here and moved it over to the left, right? We've pulled some of that data down there to get this shape. We also can think about this shape here, this like trailing off of data as the tail. Skewed left has a tail to the left, pointing to the left. Okay. It's missing its right side. There should be a tail over here that was here before. So that's one thing to notice. The other thing to notice is that when we have data that's skewed left, we're typically going to see the mean. So I'll use X bar. The mean is less than the median. Okay. All right. So far, so good. All right. So let's do something else. Let me undo the changes in data that I made. Okay, so this is skewed left. I'm going to leave skewed left up there so we can compare it to what happens when we skew in the other direction. So I'm going to undo the data. You'll see the histograms start to repopulate on the right-hand side. So all those data are back where they began. So this is no longer skewed left. I'm leaving this definition up here. Let's do the same thing, but in the other direction. So I'm going to take some of the data from the bottom and start moving it to the top. So again, all I'm doing is changing these lower data values, the 4s, 5s, 6s, and 7s, 7s and 8s probably, and moving them up into the 11, 12, 13, 14, 15 region, okay? And if you watch the histogram, you'll see things moving over there, right? Okay, that's pretty good. Okay, all right, so again, same idea. We've now created a histogram where we see this, oops, give me 1 second, why is that? Sorry, it's not letting me draw for some reason. Oh, I think I've not picked. Maybe it doesn't want to let me draw anymore. There we go. Okay, sorry about that. So we've got now data that is skewed right. All right, there's a tail to the right. And now, if you notice, the mean is larger than the median, right? Notice they've both increased, right? If you look down here at the originals, they've both gone up, but the mean has gone up much more, which is what we suggested last time, right? That the mean tends to react stronger to data, to the movement of data, right? So we had all these data down here on the left, moved over here to the right, okay? And we get this skewed right diagram. Okay, so I think that's it for this one. Yeah, that'll be it for now. I will talk to you guys next time.